Welcome to Year 1 Mechanics, Chapter 10.5, Connected Particles. Finally, a lesson where something is a bit more exciting, something a bit more dynamic going on. Which, when you hear the word dynamic, exciting from a teacher's point of view, it means more likely to be examined. So, this part of the chapter is where most of the exam question will come up, and 10.6, 10.5, 10.6 are the parts where exam questions are likely to come up. Okay, so the real give you a bit of real taste of what mechanics could look like. So in this lesson, what we're looking at is are scenarios where one particle is pulling the other particle as a connected particle. For example, you can think of it like a car with a caravan at the end attached to a caravan at the end, like a tow bar in the middle. Or you can think of maybe if you were in London, you probably central London, you would have seen those human bicycles. A person in the front pulling someone sitting in the back. So that's a connected particle. Okay, or think of it like a relay. When you hold someone's hand, I don't know what relay. You hold someone's hand, you run together. But anyway, if you're pulling someone in the back, that kind of thing. So that's basically a particle in the front pulling a particle at the end, at the back. That's a connected particle question. That's a scenario we're looking in here. You can fulfill any kind of imagination you have in your brain, but it doesn't matter because what it matters is what we look at examples. But when we have multiple connected objects, it moving in the same direction, so we're moving in the same direction. When we're moving in different direction, like a pulley, we'll look into that 10.6. But this lesson, same direction. So that's what we need to do. We need to consider particles as a single system together, right? Second of all, then you're gonna consider it separately. So it's like a two steps. Step one, step two. Okay, so that's step one, step two. So let's have a look. Example: two particles, P and Q, of masses 5 and 3 kilogram respectively, are connected by a light inextensible string. So I'll draw a diagram what it looks like in here. So we've got particle P. Let's use a square, like using a rectangle P. Okay, and then Q in here. Q is a bit lighter. So P is 5 kilogram and Q is 3 kilogram. Okay. They are connected by a light inextensible string. That means a string in the middle. P is pulled by a horizontal force of magnitude 40 Newton. So that means to the right. Along a rough horizontal plane. A rough means there's friction. So I mentioned that before. Probably doesn't matter much now because you're told a frictional force, but later on year two you'll be asked to calculate friction by yourself. So that becomes suddenly becomes a keyword. So experience a frictional force of 10 Newton. So experience a frictional force of 10 Newton. Now we know both particles going that way. How do I know that? Because they both go in the same direction, right? So if I'm going to write, therefore the friction must be towards the left. That's 10 Newton in here. Okay, and particle Q experience a frictional force of 6 Newton. That's fine. Okay, find the acceleration of both particles. Um, Now let's put in some forces in there. So let's put in some forces. We know particle on the plane, okay, will have two forces. We have a reaction, also a reaction. Now, because these two reactions are different, I'm going to call it RP and RQ. Okay, and then we also have 3G, the weight, and 5G. Now, to be honest, these forces not going to matter in this question. The reason being is that acceleration is horizontal. That means when we consider F equals ma, we're just using, x direction horizontally anyway. So the vertical forces are not going to matter. But just for your reference, we know RP equals to 5G and RQ equals to 3G. Now this will matter next year in year two mechanics where we look at the friction. But anyway, for now, it doesn't matter. So find the acceleration of a particle. So do you remember what I said at the beginning? The two steps. The first step was going to consider them as a single system. So question A. Now, because the two particles are moving together, it's a light inextensible string. That means the string is not extendable. That means if P moves in a certain speed, so does Q. If P accelerates a certain speed, so does Q. Okay, so they'll be in sync because the string is inextensible. So no matter how fast or how far P has traveled, Q will be moving in sync with P. So anyways, therefore we're going to consider the whole system. So we're going to consider it. Okay, consider whole system. So what does that mean? That means we are going to put P and Q together. Okay, so we can think of it like P and Q together. Okay, P and Q together, just like nuggets and ketchup. Right, or chips with ketchup, not brown sauce or not vinegar. Right, P and Q. So in total, with 8 kilogram. And in the front in here, we've got 40 Newton. Okay, at the back in there, we've got 6 Newton. And then we also have 10 Newton. So altogether, the experience is 16 Newton of friction. All right. So we'll consider the whole system. We use F equals ma. Okay, so going to the right. So F is 40, take away 6, take away 10, equals the mass 8. The total weight, the total mass is 8. 8 times acceleration. So if you do the calculation, 40 minus 6 minus 10 is 24. 24 divided by 8 is 3 meters per second squared. That's the acceleration. That means they're both moving at 3 meters per second squared. Okay. There's something actually I forgot to mention about is, sir, you have not put anything in the middle of the string. What forces are in the string? If you remember what we talked about very early on, okay, about string, forces in the string, I think we talk about, hopefully, do you remember this? We talk about when the string, look at this hangman and hungman, when the string is taut, we have tension. And that's the force we have inside the string. We have tension. Now, which way though? So this one I'm going to explain. Now, for P, okay, for P, if you think in this perspective of P, Q, when you move forward, Q is like a liability to you. It's like a burden because you're pulling a weight. Therefore, you will feel the string is pulling you backwards. Okay. Now, however, for Q, if you think about in Q's perspective, the fact that you're still moving forward, just like Santa Claus being pulled by the reindeer, you will. It's a reindeer that pulling you forward. As Q in here, P is pulling you forward. So therefore, for Q, the tension will be going that way. Okay, and that's why you'd be thinking, part A, where's the tension gone? The tension cancel each other when we consider them as a whole system. Therefore, we do not include tension in the calculation. But if you really want to, you can put a tension in here and then a tension in here. The forward tension is by Q and the backward tension is by P. But you can see T and T will cancel out. Therefore, we didn't include that. Okay, so just to make sure you're aware of that. Part B, find tension in the string. Now, part B, to find tension in the string, once we've considered particle as a single system, what do we do next? We consider it separately. So, part B. I'm going to do it here. Okay, part B. So we either consider P or Q. So I'm going to show you both. You just have to do one. Okay, we'll consider P. So let's have a look at the particle. We'll just do P. Okay, so for P, what are the forces on P? We've got 40 Newton. We've got tension pulling backwards. We've got a 10 Newton pulling backwards. We know we're moving at 3 meters per second squared now. So F equals ma on the x direction towards the right. So 40 minus T minus 10 equals the mass 5 kilogram times 3. So 30 minus T equals 15. So if you rearrange it, T equals 50 Newton. Okay, so or what about if you consider Q? Okay, if you consider Q is the same thing, I'll show you. And I mean, same value of T, same thing means same value of T, but different calculation, of course. So we've got Q with 3 kilogram. So pulling forward, we've got tension, and then backwards, we've got 6 Newton. So using F equals ma, we know Q is also moving forward with 3 meters per second squared. F will be, because we're moving to right, so it'll be the right force, take away left force, equals the mass times acceleration. So T minus 6 equals 9, T equals 50 Newton. So you can see, same thing. Okay, same answer. So no matter which one you calculate. So you can see it's basically 2 steps. First step, consider the whole system, P and Q combined. Second step, consider separately, either P or Q. Right? As long as you include all the forces in each particle, you'll be fine, using F equals ma. Part C. Explain how the modeling assumption that the string is light and extensible have been used. Now, there are 2 assumptions in here. Okay, I did explain about inextensible. What about light? So, everyone knows my writing is not very nice, so I'm going to type it up. Okay, pleasure for you. So, part C. Okay, so string is light means the mass of the string is neglected. Okay, so or you can say or tension is the same across the whole string. That means the string, there's no mass in the string, which in real life we know is impossible. When a string has a weight, then maybe the string is the string maybe is heavy on one side than the other. That obviously affects the calculation. But anyway, so string is light means the mass of string is neglected. What else? Inextensible. Inextensible string. It means the acceleration for both particles are the same. That means they're moving in sync. Okay, that's what it means. Right? Next one. Oh, practice question one already. Okay, practice question one. Okay, so what I want to do is, okay, read the question and answer. Okay, and do part A first. Once you're done with part A, then you play the video and check your diagram with me. Have a go. When you're ready, press play. So there's a complete diagram with the forces as well as the acceleration. I do like to put acceleration there just to remind myself, okay, acceleration is horizontal. That means any vertical forces will be balanced. So RP, RQ, 2G, 8G are not really necessary for this question, but again, it's a good habit to know that they exist. It's just not relevant to this calculation, but it doesn't mean it doesn't exist. So we've got tension pointing opposite each other. I mentioned this just now, and it's a F putting forward. So that's the whole force diagram. Okay, so have a go part B and part C. Okay, or actually have a go at the rest of them, B, C, and D. Obviously, that means typo in here, B, C, and D. So have a go. If you're ready for the, you have a go. Whenever you're ready for the answer, you can press play. But otherwise, if you need some help, okay, have a look into the previous example. What do we do? Consider whole system first and then consider individually. So pause video, have a go. When you're ready for the answer, you can press play. So here's the answer for part B, 4 Newton, and part C is 0.8 Newton. If you got right, okay, you can move on to the next part. But if you got wrong, I'm going to go through it with you, okay? First of all, consider whole system. So we're going to consider whole system. You can draw a diagram if you want to. I'm just going to show you. So altogether, P plus Q, you've got a 10 kilogram. We've got friction, and not got friction, sorry, we've got force pointing forward, we've got tension pointing to right, and we've got tension pointing to left. And we know the particle is moving by 0.4 meter per second squared. So using F equals ma on the x direction, I can do F plus T minus T equals 10a, 10 times 0.4. The two cancel out, so F equals to 4 Newton. Simple. Okay, part C, you can either consider P or Q. If you consider P, for P, that's 8 kilogram. We've got force pointing forward, and we've got tension pointing backwards, and we've got 0.4 meter per second squared. So F equals ma. So force pointing to right is F minus T equals 8 times 0.4. Now note the mass of P is 8, not 10. F we've calculated is 4, so 4 minus T equals to 8 times 0.4. I think that's 3.2. So if we rearrange it, T equals 0.8 Newton. But if you can see the Q as well, that's perfectly fine. Q might be actually simpler in this case, because if you look at Q, there's only one force acting on it, which is tension, right? And then we know the particle is moving to the right by 0.4 meter per second squared. Q is 2 kilogram. So using F equals ma, the only force is T, the mass is 2, A is 0.4, so T equals 0.8 Newton. Both way works. Part D, explain how two model assumption light extensible. We've just done that. You can just copy it from previous example. Okay. Right. Next type of particle. Next type of connected particles. Newton's third law. So there are 3 laws from Newton. For every action, there is an equal and opposite reaction. So, therefore, when two bodies A and B are in contact, if body A exerts a force on body B, then a body B exerts a force on body A that is equal in magnitude and acts in opposite direction. Sounds very confusing, isn't it? In simple words, imagine that's you, or maybe your sibling, probably better. Your sibling lying on the floor, okay? You stand on there. Yeah. Yeah. Okay. It's a smile because your sibling have no choice but lie on the floor, even though it's crying inside, but it's still a smile on the outside. That's the function of a sibling. A function? I didn't say this. Maybe it's a Freudian slip. I don't know. Anyway, so that's you. Okay. When you stand on there, okay. Now, when you stand on your sibling's body, what force are you exerting on this body? You're exerting the weight of yourself, right? You're standing on there. That means you're exerting force on the sibling's body. That's the force you're exerting on it. But in return, okay, what does your sibling offer? Your sibling offer a reaction, a support force. Now it's actually here, but what we tend to do is put it on top. So that's a react. But anyway, it doesn't matter. So the reaction. So it's a support force. So that's a weight, your own body weight, so body weight. But in return, they're giving you a reaction force, which is also a support force. Okay, so it's supporting your sibling's body is supporting the weight of yours. Okay, or sometimes if you're really angry, some people punch the wall. I don't know why to do that because it really hurts. So why do I know? Because I've done it before. Right, so that imagine that's you. Okay, we're gonna really angry. Okay, and really sad. So one day we decide to punch the wall. Okay, so that's your hand. Okay, so you punch the wall. Okay, so when you punch the wall, you are obviously exerting force to the wall, right? So that's a punching force. Okay, so exerting a punching force in the wall. But the wall, of course, is not going to cave in. The wall is made with really strong material that's not going to break. And what happened to you? What do you feel straight away? You feel pain. Why do you feel pain? Because the force is giving you a reaction force backwards. And what happened? And there's blood dripping in here. That's why. So you could say, the blood, the damage that you do to your fist is by yourself, but not the war. You can blame the war if you really want to. Okay, just like you haven't done your homework and you blame your siblings for not distracted for distracting you to do your homework or whatever. But deep down, you did not do your homework because it's all your fault. You did not find the right time to finish all your homework. Same in here. When you punch the wall, you feel pain in your fist, and that's because of your fault. If you don't punch the wall, you don't feel the pain. If you punch the wall give it back a reaction to you, and it hits and it hurts your hand, and that's why you're bleeding. Right. So that's what we talk about in here. Okay, that's Newton's third law. How does that apply? Well, let's have a look at this one. Okay. Example: a light scale pen is attached to a vertical light inextensible string. The scale pen carries two masses, A and B. The mass A is 400 gram. Now I have kindly changed the 400 gram to you for 0.4 kilogram. Sometimes the exam question is not as kind as me. I know. I'm kind. So I'm not kind. And 0.4 kilogram, just make sure you remember grams change to kilograms in exam. 600 gram changes 0.6 kilogram. A rests on top of B, just like you resting on a sibling. As shown in diagram, the scale pen is raised vertically. Raised vertically means we know it's going upwards. Okay, so that means we know going upwards by 0.5 meter per second squared. Find the tension in string. Where's the tension? Well, we know tension is here because the scale pen is pulling upwards. Tension is always pointing to the source. Okay, so remember the hangman, the tension is always pointing towards the source of the string. So the string comes from the ceiling, therefore the tension pointing upwards. Same in here. Okay, so no matter if you're dropping or it doesn't matter if you're going down like a lift. It doesn't matter if you're going down or going up. As long as the string is pointing upwards, which should always be, the tension will always be pointing upwards. Well, the string is released from the ceiling, therefore the tension will always pointing upwards. Okay, so find tension in string. Well, what we can do is same thing. We consider whole system. We consider whole system. How does it work? Well, think of it like a scale pen. Okay, and we've got tension pointing upwards, and in here we've got a 1 kilogram block. Okay, so we're going upwards by 0.5 meter per second squared. So we're using F equals ma upwards. Okay, then we have what else do we have pointing downwards then? I nearly forgot. Where's that? That with 1g. The weight, 1 mg. So F equals ma, t minus 1g equals the mass, 1 times acceleration, 0.5. So G is not a variable. G is 9.8 equals 1 times 0.5, 0.5. At the 9.8, T equals 10.3 Newton. That means if you want to calculate the material that's required for the string, in this, let's say to lift this up, the string must be able to withstand at least 10.4, 10.3 Newton of force for the string not to break, right? Part B, find the force exerted on mass B by mass A. So that's what we'll talk about the sibling situation like previous one. So what force is exerted on B by A? So let's have a look. Okay, so particle A, that's A, 0.4 kilogram, and we've got B, 0.6 kilogram. So in between them, let's have a look. So A is exerting a 0.4 G to B because that's the weight of A. And in return, B has provided a reaction force. So when they're asking you, find a force exerted on mass B by mass A, they talk about the 0.4 G. But it's not as simple as that. The reason being is because it's moving. Now, if it's not moving, okay, so I do want to put in here, okay? If not moving, R would equals to 0.4 G. But since it's moving, we have to take that into account. So we know it's moving up by 0.5 meter per second squared. So we do F equals ma upwards. So we've got R take away 0.4 G equals the mass of A, 0.4 times 0.5, because we're looking into A. So I know why. Okay, so I mean, does not say the question say force exerted on B by A. Why are we looking into A? Because the force exerted on B by A is being calculated as the reaction force. It's not the 0.4 G. The 0.4 G, it is part of the calculation, but because we're moving up, therefore the reaction given by B is not the same as 0.4 G. So we're looking into A. Okay, so we are looking into the mass of A. So R minus 0.4 G, put in the calculator. So 0.4 times 9.8, which is 3.92 equals 0.2. So I'll add together 4.12, 4.12 Newton. Okay, that means A has exerted 4.12 weight into B. Okay, part C, find the force exerted on mass B by the Scalepan. So we're looking at B and Scalepan, but A is on top of B. Therefore, we cannot separate A and B. We cannot just single out B. So we have to consider A and B together on the Scalepan. So what it looks like in part C, I'm just going to do the slide in here. Okay, so we'll look at it. A and B combined. So A and B, and this is Scalepan. So what forces are exerted on there? Well, A and B combined together has given 1G because it's 1 kilogram, right? So that's 1 kilogram. So 1G. And in return, the Scalepan has given reaction back to B. So that's a reaction back to B. Yeah. So reaction back to B, A and B together. So again, we're moving up by 0.5 meter per second squared. So F equals ma upwards. I'll take away 1G equals the mass 1 times 0.5. So R equals to 10.3 again. Okay, I know it's slightly confusing this one, but I will just explain again. Part A, find that you consider the whole system. Okay, that's not a problem. Part B, find the force exerted on mass B by mass A. We know between A and B, A is exerting a weight onto B. However, that's not the end of it because the particle is moving upwards. Therefore, if you think about like the in a theme park where one of those, what do we call those machines where you just decelerate really quickly, just drop really quickly and go up very quickly, just drop. I can't remember those names of the machine, the rides. Anyway, but you feel as you go down quicker or go up quicker, you feel the weight. If you go down really quick, if you dropped really quickly, you feel that your mass, your weight is disappear. You feel a lot lighter, right? But if you go up by very quickly, you feel your body suddenly feel heavier, and that's the reason why, because the force act on you is different, depends on acceleration. So even though the weight is 0.4 g going downwards, however, the support by B given to A is not just it's not 0.4 g. Okay, it's actually R. So using F equals ma on A particle A, so you get 4.12. That means B is actually providing 4.12 Newton. So if you do 0.4 g is 3.92. So what does that mean? That means when you're going up, actually B is providing you more weight than what you are experiencing. Imagine you're A, you are you are providing 3.92 Newton to B, but in return, when as you're going up, B is actually providing you 4.12 Newton of force, supporting you. Therefore, that's why you feel heavier because even though you only were 3.92, but you're given 4.12 instead. Okay. Part C, find the force exerted on B by the scale pen. So B and A, you cannot separate B with A. So when you say it's by the scale pen, so if you look at the interaction between B and the scale pen, we cannot ignore A when it comes to B because between B and scale pen, A is on top of B. Therefore, we consider B, A, and B together. Okay, there are a lot of little details in here that you might want to write down. Okay, so any question? Yes, there's exam practice. Okay, pause the video. Okay, draw a diagram first. Draw a diagram. When you're ready for diagram, okay, let me put down here. Okay, draw a diagram first. When you're ready for diagram, you can press play. So here's a full diagram. First of all, you've got 50 kilogram, the woman, and then the weight of the lift, the mass of the lift, the tension always pointing upwards. Now you can see in here deceleration. Deceleration means A is negative. We're still moving upward, but we're just decelerating. For example, when you on that maybe on the lift, you're approaching a floor, upward upstairs, then the lift will decelerate. Minus 2 meters per second squared. So the total overall weight going down will be 950 plus 50, 1000 G. So find tension of the cable. To work out tension in cable, you use F equals ma upwards because the lift is going upwards. So the force will be T minus 1000 G. Oh, actually, sorry, my bad. I shouldn't give it out. Pause the video. Have a go at the question part A and part B. When you're ready for the answer, you can press play. The answer is 7,800 for A and part B 390. It was just a habit from me as a teacher. You just go for the question. But actually, I forgot. It's not about me. It's about you. It's about you who are able to do the question, not me. So next time you see me going for the answer, you should pause the video directly and stop listening to me because you should try it first before listening to me. Yes, that's what a good student would do. So if you haven't done this before, if you haven't done this in this question, you're not a good student. So anyway, now hopefully let's go for the answer. If you go right, well then that's the end of the lesson for you. But if you don't, let's go for it. So T minus 1,000 G equals the mass combined 1,000 times A minus 2. So T minus 9,800 equals that's minus 2,000. So when you plus it, you get a 7,800 Newton. Okay. Part B. Find the magnitude of the force exerted on a woman by the floor of the lift. So what is happening? Well, we just want to look at the woman. Okay. Look at the woman mathematically. Okay. Don't think something wrong. So what do we have in here? For the woman, we're exerting 50 G. But by the lift floor, we are having reaction in here. And what's more is that the lift is moving upwards by 2 meters per second squared. So we just single out the woman. Single out the woman. Or look at the woman. Too many things going wrong in here. So we use F equals ma going upwards. So we've got R, take away 50G equals 50 times negative 2. So R equals to minus 100 plus 50 times 9.8 is 490. Therefore, R equals to 390 Newton. Okay, and that's the end of the lesson.